Hi everyone, this is P. Bhartesh from Institute of Aeronautical Engineering. I am standing in Data Science A section. Today my topic is diagonalization of complex symmetrical matrix. Diagonalization. An end-to-end matrix A is diagonalizable if it is similar to a diagonal matrix. That is, if there exists an invertible end-to-end matrix C and the diagonal matrix D such that A equal to C inverse DC. Or diagonalization. The conversion of matrix into diagonal form is called diagonalization. The eigenvalues of a matrix are clearly represented by diagonal matrices. The diagonal matrix is a square matrix in which all the elements are 0 except the principal diagonal elements. Complex matrix. An M×N complex matrix is a rectangular array of complex numbers arranged in M rows and N columns. The set of all M×N complex matrices is denoted as or complex. For example, A equal to A plus IB, C plus ID, B plus IA, C plus IA, C plus IB, A plus IC, C plus ID, B plus ID, B plus IB. This is the form of complex matrix, where A is a real number and B is the imaginary number. Complex matrices. Linear transformations are defined in exactly the same way, and a complex matrix is simply a matrix whose entries are complex numbers. There are two important operations defined on the complex matrices: the conjugate and the conjugate transpose, also known as the Hermitian transpose. Symmetric matrix. A symmetric matrix is a square matrix that is equal to transpose of itself. If A is a symmetric matrix, then it satisfies the condition A equal to A transpose. For example, B equal to 2, 3, 6, 3, 4, 5, 6, 5, 9. Therefore, by changing the rows and columns, we get B transpose that equal to 2, 3, 6, 3, 4, 5, 6, 5, 9. We can see that B equal to B transpose. Then they are then this matrix is called symmetric matrix. Diagonalization of symmetric matrix. Procedure of diagonalizing a matrix is as follows. Assuming that dim E lambda A is equal to multiplicity of lambda for each distinct eigenvalue lambda, we find a basis for E lambda A. The union of the basis for each eigenspace is then basis of eigenvectors for R power n, and the matrix P whose columns are those eigenvectors will satisfy P inverse AP that equal to D. D is a diagonal matrix whose diagonal entries are the eigenvalues of A. If A is symmetric, we know that eigenvectors from different eigenspaces will be orthogonal to each other. If we further choose an orthogonal basis of eigenvectors for each eigenspace, which is possible via Gram-Schmidt procedure, then we can construct an orthogonal matrix basis of eigenvectors for R power n. Furthermore, if we normalize each vector, then we will have an orthonormal basis. The matrix P, whose columns consist of the orthonormal basis vectors, has a name. Definition: a matrix P is called orthogonal if P in transpose equal to P inverse. A matrix P is orthogonal if and only if the columns of P from an orthogonal basis for R. A fun fact is that if the columns P are orthogonal, then so are the rows. But this is not true. If you ask for the columns to be merely orthogonal, for example, the columns A equal to 105 minus 2, 1, 2, 1, 2 minus 1 are orthogonal. But as you can check, the rows are not. But if we normalize the columns, we get P equal to 1 by root 6, 0, 1 by root 30, 2 minus 2 by root 6, 1 by 5, 2 by root 30, 1 by root 6, 2 by root 5, minus 1 by root 30. As you can confirm, is an orthogonal matrix. An end-to-end matrix A is said to be orthogonally diagonalizable if there exists an orthogonal matrix P such that P transpose AP is diagonal. The above definition leads to the following result, also known as principal axis theorem. A careful proof is quite difficult. Unwanted from this book. The hard part is showing that the symmetric matrices are orthogonally diagonalizable. There are a few ways to do this, most requiring induction on size the matrix. A common approach usually uses multi-variable calculus. If you are reading this along with the book of Nicholson, there is a gap in his proof. The induction step, he assumes that existence of real eigenvalue A but has to be proved. Real spectral theorem. The following are equivalent for n into n matrix A. A is symmetric. There is an orthogonal basis for R power n consisting of eigenvectors A. A is orthogonally diagonalizable. Determine the eigenvalues of A equal to 5 minus 2 4 minus 4 2 minus 2 to 8 minus 2 minus 4 2 minus 2 5, and we can find an orthogonal matrix P such that P transpose AP is diagonal. By solving the problem, given that A equal to 5 minus 2 minus 4 2 8 minus 2 minus 4 2 minus 2 5, by writing the characteristic equation by formula A minus lambda I, that of A minus lambda I equal to 0, we get the characteristic equation as lambda cube minus 18 lambda square plus 81 lambda equal to 0. By solving the equation, we get lambda equal to 909. By taking the first eigenvalue, lambda equal to 0. By substituting the eigenvalue lambda equal to 0 in A minus lambda I into x equal to 0, we get two equations, that is 5x1 minus 2x2 minus 4x3 equal to 0 and minus 2x1 minus 8x2 minus 2x3 equal to 0. By solving these two equations, we get x1 by 2 equal to x2 by 1 equal to x3 by 2. Therefore, for lambda equal to 0, eigenvalues are 2 1 2. Case 2. By taking lambda equal to 9, we get three equations, that is minus 2x1 minus 2x1 minus 2x2 minus 2x3 equal to 0, minus 2x1 minus 2x2 minus 2x3 0, minus 4x1 minus 2x2 minus 4x3 0. These three are identical equations which can be solved by taking any one of them as k and k1. Let x1 be k and x3 be k1. By solving the equation, we get x2 equal to minus 2k1 minus 2k1. By solving this equation, minus 2x1 minus 2x2 minus 2x3 equal to 0, we get x2 equal to minus 2k minus 2k1. The eigenvalues for lambda equal to 9 equal to x1 x2 x3, that equal to k minus 2k k minus 2k1, that is k into 1 minus 2 0 plus k1 into 0 minus 2 1. Model matrix P equal to, then you can find the model matrix by substituting all the eigenvalues, that is eigenvalue in case 1 is lambda equal to 0, that is 2 1 2. By substituting in the model matrix, the first column is the eigenvalues of lambda equal to 0, and the second two columns are eigenvectors of lambda equal to 9, that is 1 minus 2 0 and 0 minus 2 1, 1 minus 2 0 and 0 minus 2 1. The diagonal matrix is P inverse AP, that is 0 0 0 0 9 0 0 0 0. We can recheck the diagonal matrix by the eigenvalues. The diagonal elements should be eigenvalues of the matrix, that is 0 9 9. This is eigenvalues of matrix A. Diagonalization of complex symmetric matrix. At any rate, a complex symmetric matrix M is diagonalizable if and only if its eigenmatrix A can be chosen so that A transpose MA equal to D and A transpose A equal to I, where D is the diagonal matrix of eigenvalues. In other words, there is a complex orthogonal rather than unitary matrix of eigenvectors. Its diagonalization of symmetric matrix is unique. Diagonalization is not unique in general. but unique up to permutation of the diagonal entries in D and multiplies of the columns of U. Conditions. If A is a matrix has a complex eigenvalues, it is not diagonalizable. At any rate, complex symmetric matrix M into n is diagonalizable if and only if its eigenvectors matrix A can be chosen so that A transpose MA equal to dA transpose MA equal to D and A transpose A equal to I into A transpose A equal to I, where DD is the diagonal matrix of eigenvalues. Based on this fact, one can construct 22 complex symmetric matrices that are not diagonalizable. Step to diagonalize complex symmetric matrix. The complex symmetric matrix that is not an Hessian input matrix is diagonalized in two steps. First step, the matrix is tridiagonalized by a series of n-2 generalized Householder reflections, where n is the rank of the input matrix. Second step, the tridiagonal matrix is diagonalized via the generalization of the chasing of Bloch technique, which is an iterative process utilizing an implicitly shifted initial rotation followed by n-2 generalized Household reflection. For complex symmetric matrices, these are not Hermitian. One cannot use the usual definition of Householder reflection, which is designed for potentially complex Hermitian matrices. In order to apply the Householder reflections to a complex symmetric matrix, we turn to the indefinite inner product, which avoids complex conjugation x comma y star equal to x transpose dot y x comma a y star equal to a transpose xy, where a transpose is the transpose of A. The Householder matrix employing the indefinite inner product 1 is HV is equal to 1 n into n matrix minus 2 v star v cross vt transpose. Householder reflections and tridiagonalization. It is possible to use a variety of methods to bring complex symmetric matrix into tridiagonal form. Of instance, Klum and Wilby have shown that it is possible use to Lachnow's method to diagonalize complex symmetric matrix. Yet we have chosen to employ generalized Householder reflections to accomplish the same goal. The elegant Lachnow's method have been described and analyzed in detail. These methods are primarily useful when a conclusion. The symmetric matrix are diagonalizable because there is an implicit algorithm for finding a basis of eigenvectors for them. The key fact is that the unit ball is compact. This means that we can solve maximal problems for continuous functions on it. Thank you.